So yeah, welcome everybody. So for some reasons, my camera is not showing, so I will just switch to the integrated webcam. Okay. For some reasons, the camera is not working, so I'll just switch to my laptop's camera, which is not very clear. So you probably won't see my face clearly here. But can you hear me? Can everyone hear me?
Yes, I can hear.
Yes,
Okay, good. So we'll start our class very soon. You're all welcome to another session. Okay, I'm coming. So I'm going to share the window. Okay, can you all see the window I'm sharing right now?
Yes, I can see.
Okay, good. So from the previous class, I remember a question was being asked about this word to vec. So we briefly talk on that right now. The word to vec model. Where is it? Okay. Okay, over here. So as this is not really a code intensive class, the main purpose of this class is for us to really get grounded on various machine learning concepts and how we can use it in our everyday life to make it as simple as possible. So what VEC is, it's a model. Yes, the machine learning model for processing words in data sets, synthesis data sets for training different models. It's especially useful for LLM, large language models. So what it does is that it takes a data set. In this example, the synthesis here is the data set and it contains two syntheses. I love machine learning and machine learning is fun. This is a very small data set. In real life, the data set will be very, very large and the machine will be able to know the relationship between different words. Just like we as humans, we understand the meaning of words and we know what those words mean to us. So we have a semantic understanding of words, how words are related to each other. In a machine world, this is how a machine understands words. It understands it in the form of a vector. Now, each of these, the sentences you are seeing here represents the data set itself, which is what has been provided already. The vector size here is just another parameter that just represents the length, the size of the vector. It's telling us that the vector is a 10-dimensional vector. That's what it means. The Windows 2 here is just what it does is for context, is for understanding context by looking at two words that are before and two words that are after it. That's what this Windows 2 for, is for the machine to understand the context of the word by looking at the surrounding words. The Windows 2, that's what that Windows 2 means. The minimum count just means that the minimum count of words, the minimum count that the word must appear for it to be considered by the model. So if it appeared once, it's going to be considered by the model. Why this worker 4 is just talking about the CPU calls that is going to be used during the training. So more workers means more memory usage and more CPU usage that is going to be used during training. So this is how the continuous vector space works. And this is how a machine understand individual words compared to humans that we just have a sense of how those words are related, how those words mean, what they mean to each other. This is how a machine understands it, by converting those words to vectors. So over here, we are trying to look at, considering the synthesis data set above, we are trying to print out the vector of machine and the vector of learning using that word-to-vec model also. So the word-to-vec model looks at all of the dimensions, all of the different dimensions, the 10 dimensions of each word vector, of each vector of the words, and sees how they are related or unrelated. Is with this vector, this 10-dimensional vector, that the machine will know the relationship between machine and learning according to the data set that it has been trained on, synthesis. So now moving on to image data. On this, on my cargo notebook, I've already uploaded some data there, like this elephant. This is just a picture of an elephant. Let me click on it and let it load. This is just a picture of an elephant. So it's loading. You can see, if you can look at it from here, you can see that it's a picture of an elephant here. And this is just an audio here. So let me close this now. After seeing that is a picture of an elephant, from TensorFlow library, Keras module, preprocessing submodule, we import the image. We're trying to import image, probably the images that are already there, preset images. But in our own case, we're going to use the elephants that I downloaded from the internet, try to see how it can predict. This is just an example for us to see how a machine understands. This VGG system that you are looking at here, it's a machine learning model. It's a deep learning model specifically for image recognition. So when I ran this entire code, it was able to predict that that image you are seeing here is an African elephant. There's a 74% probability. So you can see that the machine actually understands things with numbers. It understands things with probability. So based on how this VGG 16 has been trained in the past, it's been able to dictate that there is a 74% probability that the image is seen there is an elephant. And we can all see how it's being loaded. First of all, we need to load the image and store it in the img container, and then we need to convert that image to an array. An array is just a series of numbers following each other. And then we need to preprocess it. After preprocessing it, and then we call on our model, and then we try to predict it using that model.x, what you've preprocessed already, before it would then tell us the probability that this is an elephant. So moving on, audio data too are also broken up into samples in our previous lessons that I've explained, and they use techniques such as the Fourier transform to convert samples into frequency domain features that captures the patterns in the sound wave. So this is the audio, it's just an audio file, it's a simple sound that is making. So when you print it out, you can see how it's being represented in numbers. This is how audio is being represented in numbers. So when you are talking about audio, this is what the computer sees in the background. So categorical data, as we said in our previous lessons, that it can be converted to numerical data through either one-hot encoding or label encoding. So this is an example of how one-hot encoding can be used for converting categories like color, for instance, red, green, and blue. Red is converted to this, green is converted to 010, and blue is converted to 100. Automatically is being done by that. Is under the preprocessing module of the sklearn library. And so yeah, this is just showing us how we can actually set those numbers by ourselves if we want to. If you don't want to use, if you don't want it to be set automatically by the one-hot encoder class. You can also use label encoder. This label encoder class also, it just assigns a single integer to each of the categories. Like now here, 2 is assigned to blue, 1 is assigned to green, and 0 is assigned to red. And it's also very important. It's also very important for you to know that using a label encoder is going to be more appropriate for ordinal categories. That is, categories that follow a particular order, such as the educational level. For instance, educational level follows a particular order. So it's very appropriate to use it for ordinal categories, not just any category that doesn't have an order. So the machine will not think that there is an order where there's no order. So in such a case where we do not have an order, such as ordinary categories, we can just use this our one-not encoding for it if it's not ordinal. So these techniques can just help in transforming raw data into a suitable format for the machine learning, enables it to learn and make prediction. So moving on to feature scaling, we've talked about normalization, and we've talked about standardization between a standard deviation, normalization within 0 and 1, putting values between zeros and 1. Although we need to understand something. It's not every model that is affected by feature scaling. There are some models that are critically affected by feature scaling, while other models are not critically affected by feature scaling. Examples of some models that are affected that you need to use feature scaling. If not, your prediction is going to be off. The model performance is going to be off without feature scaling. These models include the support vector machine, the k nearest neighbor, principal components analysis, neural network, k-means clustering, linear regression, that you are using regularization techniques with it, gradient boosting machine. All of these, they are really affected by feature scaling. And the reason is because it relies on distance measurements. Yes, all these models, they rely on distance measurements between data points. Now, imagine some data points that are in over, let's say, a particular features, we're having values of like 2 million. Let's call that feature 1. In feature 2, you are only having a maximum value of, let's say, 20. So if it's going to measure data points, it's going to assume the one of feature 1. If there was one that has 2 million and there was a value there that has maybe 20, if it's going to measure the distance between 2 million and 20, that's a lot of distance. That's a very great distance compared to a feature 2 that is just within a very small range of value. So this is the reason why feature scaling is very important in certain model like SVM, KNN, PSA, neural network, and k-mean clusterings. They are very, very important for you to have feature scaling in it. But there are some models that even if you don't apply feature scaling in it, it's not really going to be affected, like decision tree models, random forest, naive bias, and logistic regression, the ones that you are not using regularization techniques in it. So they are not really affected by feature scaling because there is no distance measurement that is going on there. It's just some rule-based algorithms following either greater than, less than, yes or no, move to the next leaf, move to this leaf if it's greater than, move to this leaf if it's less than. There are a lot of numerous videos that you can watch about decision tree to understand how it works and why it is not sensitive to the scale of the features. So over here, I just talked about some impacts of feature scaling on some machine learning. It just helps them to converge easily. So instead of focusing on the scale of those features, we are going to be focusing on the actual relationship between the features and the dependent variable, what we are trying to predict. And then I talked about KNN, Yeah, and distance calculation. Yes, because of KNN, that's the K nearest neighbor, is used for classification, and it's a supervised learning. They use the Euclidean distance. They calculate distance to find the nearest neighbor. So scales with larger range can dominate the distance calculation, leading to biased results. So you have to make sure that everything is within the same range so that equal importance can be taken for each of those features, assuming that all features are equally important. Okay, so now let's go to the very interesting aspect of it, feature selection. Now, how do you select features when you have numerous features that you are looking at and you're trying to quickly select? There's so many techniques that you can use for selecting feature. Some of them are the principal component analysis. You can also use recursive feature elimination, and you can use correlation analysis. These are the three most common techniques that we use for feature selection. Now, this principal component analysis, as much as I would like to explain and demonstrate how we can use it to select features, it's not going to be easy here because I don't have some editing. I don't have some video editors there that will really demonstrate it. What happens is that in principal component analysis, we are trying to look at angle from which there is a large variation in data. We are trying to look at the data from an angle where there is a maximum variance in the data. That is what principal component analysis is doing. So it's going to create new features or new axes or new dimensions that captures the maximum variance in the data. So we can have any number of principal components as possible, depending on how important or how much is being captured by the number of principal components that you are considering. So what this means is, let me give an example. For instance, if let's say now I've been collecting data on with my smartwatch has been collecting health data about me, and my phones has been collecting other data. I'm trying to determine the features that are most important in telling my daily mood, my mood fluctuations every day. So in my data, I'll be collecting a lot of in my data set rather, I've been collecting different data. So now let's click on this and open it and see what we have. Yeah. Let's see how we can use PCA. Although PCA is not a direct method for feature collecting, it's not a direct method for feature selection, but we can actually use it to reduce the dimensions that needs to be displayed. The main function of PCA is for visualization purposes. For instance, let's say in your data set has about 8 different features. Obviously, you cannot display 8 different features. That's like saying 8 dimension. The maximum amount of dimension that the human eyes can understand is 3. So we can only display 3 features at the same time. So where principal component analysis comes into place is reducing the number of dimensions that is required to display all of our data sets. So this is an example using our PCA, using PCA to actually scale down to actually reduce the number of features in our data sets. Now look at this. First of all, we need to standardize. Remember, I said PCA is one of those things that is affected by the scale. So we need to standardize the feature, make sure that they are all within the same standard deviation. And then we perform PCA on it, initially taking as many components as possible. So in this case, I'm trying to use PCA to rank the features in the order in which they are important, the order of importance. So this was the results. So you can see from this feature ranking that the features that were collected are the negative events, my moving, my stress, my standing, my sleep duration, the number of steps I take every day, the kilocal, the number of calorie burnt, my sleep quality, the atmospheric temperature, the AQI, that's the atmospheric, the air quality index rather, my BPM, that's my beats per minute, the positive event, and the screen time. These are all of the features that are in my data set that I'm trying to use to predict my daily mood, if I'm going to have a good mood or I'm going to have a bad mood that day. So according to PCA is trying to tell me that the most important feature there is the negative event. So what this means is that negative event seems to be the most impactful feature that is affecting my mood that I'm trying to predict. The mood there is the dependent variable that I'm trying to predict. And what I'm trying to use to predict it are the independent variables. That is the features that I'm studying, which includes the negative events, moving, stress, standing, sleep duration, steps, and everything that is in this PCA mood dataset.csv over here. So you can see you really should be very careful when you're using PCA, because PCA is unsupervised. PCA does not really care what you're trying to predict. It just looks at the entire data set itself and tries to look at the angle from which captures the maximum variation in data. You know, if you remember this picture that we used to see, it's like a meme. Like if you are looking at a number 6 from one side, it looks like number 6. If you're looking at number 6 from one angle, it looks like 6. But somebody opposite you looking at that same from that same number, it will look like 9 to the person. If you turn 6 upside down, it looks like 9. So that's similar to what is going on here. So PCA is trying to look at it from an angle where it captures the maximum variation in data. So when you are looking at data from different angle, you will notice that you are seeing different things. So what PCA is trying to do is it's trying to look at the data from an angle that captures the maximum amount of variation in the data set. That's what PCA is all about. Although this does not really have a direct real life implication. So you have to be very, very careful when you are using PCA for model selection. So moving on to a more traditional way for selecting models, which is the recursive feature elimination. So recursive feature elimination is a more direct way for selecting mode, because in recursive feature elimination, it's taking into account what we are trying to predict, which is y, the mood. The mood is our dependent variable. That's what we're trying to predict. Yx is the matrix of independent variable. So we drop the mood, since the mood is not part of independent variable. So we have to drop it here in this case. And we load the data. That's the PCA mood.csv. And then we can scale it. We have to scale it here. So you can see the model here is using linear regression for it. So it's assuming that there's a linear relationship between our features and our dependent variable here. And remember, anytime you see .fit here is trying to tell us that it's going to be trained using RFE. Now, let me explain what is going on with recursive feature elimination. Recursive feature elimination means that we eliminate a feature and then we look at the performance of the model. We record that down. To measure the performance of the model, we use RFE. You can use no, not RFE. You use our cost function here. That is the error, the mean squared error, MSC. We use our MSC to calculate the performance every time we remove a feature. So now let's say, for instance, we remove this feature, positive event, and then we calculate the MSC of the model and see how it performs. Let's say the performance was 0.7. That's let's say the R squared performance is 0.6, for instance. And then we added positive event VAC, and then we removed negative events. Let's say the performance dropped to maybe 0.5, and then we had it back. And now we remove temperature. Let's say the performance increased to 0.8. What that is telling us is that the feature that we removed previously was making the entire model worse. So that's just what recursive feature elimination is doing, is removing the features one by one and then calculating the performance of the entire model without that feature, and then seeing how each of the model performs when a particular feature is missing. So if a model performs very well when a particular feature is missing, it means that that feature is really bad for making prediction. Means that the feature must be the first thing for us to remove for us to have a better performing model. So this will continue as we've removed, let's say like the moving. Obviously moving here is ranked 13. That means that when we removed moving, our feature, our model performed the best when we removed it, meaning that it is the least needed feature in our data sets for our model prediction. So when we remove moving, we notice that our model was performing very well, which means that moving was the least important feature in our data sets. Then they continue to remove other models too and compare it. Now that we've eliminated this thing, that's just what it means. We eliminate moving. Now we have 12 left. So now we notice that as we're removing each of those features one by one, we notice that AQI was the feature that was removed that gave us the best model performance, meaning that AQI was the next worst features, was the next useless features that was there, that was being used to make an accurate prediction. I don't know if you understand my explanation. So it will continue to eliminate feature that such that the elimination of that feature will lead to a better performance. So in this way, we'll be able to rank the features based on how they are helping the model to make a good prediction. So at the end of the day, we noticed that positive event was the most important feature there. That means positive event was the most predictive of my mood. When you think about it, that makes a lot of sense. Negative events too is telling me that negative events also had a very good, it had a very good importance in predicting mood, which actually makes sense because when good things happens to you in a day, obviously your mood is going to go up. And when negative things happens to you on that day, obviously it will negatively affect your mood. So positive events and negative events are ranked really high, meaning that they have a lot of impacts on my mood. Temperature too and screen time too are also very important for my mood, because on days when there is a very high temperature where everywhere is hot, it means that it tends to affect my mood either positively or negatively. And on days that are cool, I tend to be in a better mood. Screen time too is also very important. It means that the time that I'm spending on my phone, it has a particular effect on my mood, be it negative or positive, depending on what you are doing on your phone, or how you are using your phone. So the time that you're spending on your phone can also have a particular effect on your mood. Blood pressure, that is beat per minute too, also has an effect, and sleep quality also has effect. Stress also has effect too on your mood. So with this particular feature ranking that we have here, we can begin to eliminate features that are of least importance. So the first feature that we're going to eliminate here is moving, meaning that the number of minutes or hours that I spent moving does not really have so much effect on my mood. The AQI too, that's the air quality index too. That's just to say how the air outside is breathable. It does not really have so much effect on my mood too. The number of steps I'm taking every day too also doesn't have so much effect on my mood. Sleep duration, the amount of how long I slept for the day might or might not have so much effect on my mood. So now the next question should be, how do we know how many features to remove from this using for this our feature selection, that is where our PCA comes into play here. If you look at our PCA here, for instance, we look at this, the principal components. Now, what this graph is telling us is that in the first principal component, it accounts for 20%, a little bit over 20% of all the data variations. When we add the second principal component, it accounts for 40%. You can see this is the cumulative explained variance. It accounts for 40%. When we add the third principal component, that one accounts for over 50%, somewhere here between 4 and 6. When we add the fourth one, that one was going to 60%. So we need at least 70%. So we need to add 5 principal components for us to have about 70% of the cumulative explained variance. So we need 5 of these principal components. So perhaps if we are going to select, what this means is that we should select the first 5 components, 1, 2, 3, 4, 5. So you can see how PCA is useful. What PCA is telling us is that once we select our first 5 components, we would have already accounted for about 70% of the variation in data. So if we remove the remaining components there, we are just going to lose about 30% of information, which is not going to hurt so much, but you need to be very careful. So this is where domain knowledge comes into place. Domain knowledge means that your specialized knowledge, that is, you can go and consult with a psychologist and ask a psychologist that, okay, out of all of these components that we have here, we want to start eliminating from behind. Recursive elimination. So we need to eliminate as much as possible and leave only a few components. Like, let's say we need to leave only 5 components or 5 features for our model. So somebody that is a psychologist will tell you that moving shouldn't have so much effect on your mood. You can remove it. AQI, atmospheric quality, air quality index shouldn't have so much effect on your mood. You can remove this feature. Steps doesn't have so much effect. That's true. A psychologist might agree with you. Remove it. Sleep duration. A psychologist will tell you that your sleep quality is affected by your sleep duration. So you need to add sleep duration to it, because the longer you sleep, when you have your 7 hours of daily sleep, it can positively affect your mood, because when you sleep well, your day is going to be okay, compared to when you sleep less. You are going to be having bad mood because you are not sleeping well. So your psychologist has a domain knowledge. You need to go and meet somebody that has a domain knowledge for you to guide you on the features that you should eliminate. Now, the third also common method for feature selection is also called component correlation analysis. What correlation analysis does is that it compares every pair of feature to each other, including the dependent variable that you're trying to predict. Also, you can also compare that too with other features. So if you look at this matrix here that you're seeing there, this matrix is a picture that I got from GMP. Yes, I downloaded it from GMP. GMP is just a statistical software that is also used for data analysis. So this GMP now plotted a graph to see to do is just for correlation analysis. That is, we are trying to see how those features are correlated to each other. If you notice that diagonally, all the correlation that you are seeing here is 1, 1, 1, 1, 1, 1, 1. And that is because the same features are perfectly correlated to each other. Negative event is perfectly correlated to negative events. That's why it has a correlation of 1. Mood has a perfectly positive correlation with mood. That's why it has a score of 1. Sleep quality is perfectly correlated with sleep quality. BPM is perfectly correlated with BPM. That's why we have 1. Kilocal is perfectly correlated with kilocal. That's why we have 1. So perfectly correlated features, they are very high on the correlation number. That is, they are close to 1 or even 1 if they are the same thing. So obviously, you can use it to know data that are redundant. So if 2 features are very strongly correlated. That is, they have correlation that is going over 0.75. You know that putting those two features is going to be really redundant for your model, because it's like you saying the same thing. So if you are to guess a model that, the features that is going to be correlated, you can say steps and kilocal is going to be correlated, because the more steps you take, the more energy you burn. So we would expect a high level of correlation between steps and kilocal. The same thing with moving too. The more you move in medium to high intensity activity, the more correlation you are going to have. So kilocal and moving too is going to be seriously correlated. So let's look at it. If you look at moving here, along this column here, moving, and if you look at kilocal here, you would see that kilocal and moving, they are very correlated, 0.65. That's the correlation score, almost 0.7. So they are very correlated, but not strongly correlated. But there is some correlation between moving and the number of calorie you burn per day. Same thing as steps. Steps and kilocal is also correlated, 0.628. Very, very correlated also. So there might be some redundancy in adding steps, kilocal, and moving all in the same data set, because they are highly correlated to each other. And another one that is although the correlation is not all that serious, but there's some level of correlation in it. So if you look at this one now, sleep duration and sleep quality, very, very correlated. You can see sleep duration 0.7816, sleep quality and sleep duration, they are correlated by 0.78, which is over 0.75, meaning that it's very redundant to ask sleep duration and sleep quality in the same data set, because they are measuring the same thing. They are very, very dependent on each other. So the longer you sleep, the better your sleep quality, which is true. That is why they are very, very correlated. So it will be very redundant. When I say redundant just means that you are doing the same thing over and over again. You are giving the same answer to a question. So it's redundant to have both sleep duration and sleep quality for your model. Now, there's another thing I want us to notice. If you look at this very well, if you remember in secondary school, there's one particular logical question that they used to ask us, that if A implies B and B implies C, does that mean A implies C? Well, if you think about it logically, maybe A implies C. Like logically thinking, it might imply C. But realistically, this is not necessarily true. Case in study, what we have here. Steps, the number of steps you take, it implies the number of calories you burn every day, which is true. And from the correlation analysis, you can see it. At the same time, moving implies the number of calories you burn also. So the more you move in medium to high intensity activity, the more calorie you are going to burn. So does that mean that the number of steps you take, it implies the number of the minutes that you move? Now, remember that this data was collected by my smartwatch, and my smartwatch was programmed to only count moving when I take at least 25 steps during medium to high intensity activity. That is the condition for my smartwatch to calculate moving. When I take at least 25 steps during medium to high intensity activity, what it means is that if I should just stand up now and take like 5 steps and then I sit down, it's not going to count it as moving, because it's not a medium to high intensity. So how does my smartwatch calculate medium to high intensity activity? It calculates it by measuring my cadence. Cadence is just the number of steps I take per minute. So when I take at least 100 steps per minute, or if my heart rate exceeds 64% of my maximum heart rate. My maximum heart rate is about 181, because I used to circle, so my heart rate can go as high as 181 beats per second. So if my heart rate should exceed 64% of that, then it's going to calculate the steps that I took. When I take at least 25 steps, it's going to start calculating it at that point. So you see the reason why you can take so much steps and it's not going to be calculated as moving. So it is not necessarily correlated, even though other factors are correlated with it. So now, the reason why feature is so important is because when you select the relevant features, the model will be able to focus on the important information, leading to better performance. I don't know if you guys have heard about this Occam's result. Occam's result says that the simpler something is, the more likely is going to be the truth. So just because something is complicated does not mean that it's better. Most often than not, the simpler answer is usually the best answer. So the simpler your model is, the better your model is going to perform well for you. And also, it's going to reduce computational costs, because when there's just few features to be calculated, your model will be much more efficient and is not going to cost so much to train your model. So there's the reason why we need feature selection in order to be able to have a better performing model. So moving on to what exactly regression is. So regression is just a statistical method that is used to model and analyze relationship between a dependent and an independent variable. That is what regression is all about. So there's linear regression and there's also non-linear regression. But most often we use linear regression in our machine learning. So linear regression is defined by this simple formula, which you guys are already aware of. Y is equals to, in the previous calculator image that I showed you in our previous lessons, I say y is equals to mx plus c. That is what is going on here. M here is b1, beta 1 in this case. Yc is b0 in this case over here. And this is just for error. We're calculating the error. That's what it means. There's also multiple linear regression. Multiple linear regression is just when we have multiple independent variables trying to predict a single dependent variable. So of course, we are going to have our intercepts here, which is our bias in machine learning model. And we are also going to have our B1, B2, and so on, all the way to Bn, which is our weight in machine learning model, or called slope in mathematical terms. There's also polynomial too. Polynomial is when those independent variables are having different powers. Like when we have y is equals to mx raised to power 3 plus mx raised to power 2 plus mx plus c. That is polynomial. When the x is having powers in it. That's what polynomial is. Why this ridge regression and lasso regression, they are not usually used alone, but they are used in combination with the linear regression, be it multiple or simple linear regression, to avoid overfitting. It's just a way of punishing the model to prevent it from overfitting. That's what it is. So in this logistic regression, usually logistic regression is not used for regression problems, even though there's a regression written there. Is used for classification most of the time, especially binary classification, this regression. And there's also Poisson regression also. So we all know what all of this means. They are the coefficient of slope in mathematical language, or also called weight in data science language. And then there's B0 called the intercept, also called the bias in the machine learning or data science language. And the error term is also part of the algorithm that is used for calculating MSC. That's it, that we talked about the previous time. So anytime you are hearing that ChatGPT has 18 billion or 80 billion parameters, the parameters they are talking about are the trainable parameters. And the trainable parameters are the slope and the intercepts, also known as the weights and the bias. These are the trainable parameters. So when they say ChatGPT has 80 billion parameters, what it means is that ChatGPT has 80 billion slopes and intercepts that was being derived during training. That's what they are talking about. So what exactly about regression makes computer so smart? So you might have heard about this, that mathematics is the mother of all science. And this holds true because mathematics gives birth to the remaining science. And science is how humans are so much better than other animals due to our ability to count numbers. The reason why humans are more advanced than, let's say, chimpanzees or gorillas is because we can count. We have the ability to count. We have the concept of numbers. We know how to count. We know how to calculate things. That's one of the major reasons why we are smarter than other animals. And if we can also bring this ability to a computer will become so much smarter. And this counting is just a small part of mathematics. Regression just takes it a step further. So just as you see it, a lot of things that happens in life can be explained with maths and science. So if a computer can be made to use maths in making decisions, it can be just as smart, because math explains a lot of things in life, even though they are not so obvious until it's been brought out mathematically. So in the next few minutes, we are going to really explain it, but that is going to be on our next class. This class is meant to hold for just 30 minutes. So I would like to take any questions now if you have any question. Actually, we have used an hour, not 30 minutes. So let me know if you have any questions so far based on everything I've explained now, and I'll be glad to clarify any confusion if there are. So I'm going to take the silence as there are no questions. It looks
No,
like everything I explained.
thank you very much.
Okay. Okay, so let's have the question.
Okay. Actually, I'm a little bit lost on the data you were using, your mood prediction, what
Yeah,
you use to predict your mood. So, using it from rank 1 to down to 13, you said you use the recursive, I'm forgetting the way you use that, the recursive, you
oh,
can help me with
recursive
that, please.
feature selection. Yes,
Recursive figures,
RFE.
that was what you used to do.
Yeah, to select features. Yes.
Yes, yes, sir. So you said you were removing each pictures one by one. So what the mean square error gives, that's what you're using to rank it. So that's what I want to know. Maybe I'm right in that my
Yes, yes. Oh, yes, definitely. Yes. As it's removing it, it's going to be using this mean squared error to rank it, to rank the performance of the model each time you remove the feature.
yeah, okay. So
Yes,
the
it's
one that
using
performs better is the one that is on.
yeah, it's the one that has a better either mean squared error or R squared. The one that has a better mean squared error score or a better R squared score by the time you remove
So,
it.
okay,
So
sir.
when you, for instance, yes, for instance, when you remove moving, you will notice that removing moving makes the model perform the best. So what does that tell you about it? About moving?
Now
Like
moving
now,
is
when
less
I remove,
important.
yes, exactly. It means moving is the least important, because when I removed moving, the model performed best than removal of other features that are there. So that is the logic behind recursive feature elimination. We are removing the features one by one and measuring the performance of the model. So the feature that I removed that led to the best model performance is indicating that that feature is the least important, because removing it made the model performed best. I hope you understand the reasoning behind recursive feature elimination now.
Okay, sir. I understand, sir. But one
Okay.
more thing, sir. What is that mean square or R squared? What value should we know? How do we know the one as how we explain according to
Okay,
the
she
value?
R squared
Like is
Abi.
it when
Yeah, okay, yeah. Oh, okay, okay. In the previous webinar, I mentioned that R squared, one is the best value for R squared. So if a model should give us an R squared value of 1, it means the model is perfectly fitted for the data sets that it was trained on. That means the model was 100% accurate on every prediction it was tested on. That's the meaning of R to the value of 1. But if R is reducing, let's say R is 0.5, is not all that good. 0.8, yes, that's a very good performance. But we also need to be careful too, depending on the problem, on the particular data set we are working with, or on the domain. that we are talking about here. So in some domain, a R squared value of 5 might be good enough. In some domain, the R squared value might be 8, of 0.5 might be good enough. In some domain, a R squared value of 0.8 might be the cutoff that is required for a good model. That's for R squared. Why 0? If you have an R squared of 0, what it means is that it's as good as guessing. It's just like guessing. When someone asks you to predict something, then you just guess an answer. That's what 0 means. But if you have a negative R squared, it means that it is worse than guessing. Imagine if something is worse than guessing. It's completely useless. So having a R squared that is close to 1 is always a good idea. So when each time you remove a feature, it's going to be measuring the R squared. It's going to be measuring the R squared. So the one that gave the best R squared, the feature remover that gave the best R squared, is going to be the least important feature. So now that we have eliminated the least important feature, we now focus on the remaining feature and we start the whole process again. We look for the next feature to eliminate. Probably in this case, the next feature that was eliminated was AQI. After eliminating that one, we exclude it from it and we focus on the remaining 11 features that is there. Then we look for the next one to eliminate. We continue the process until we reach the number 1 most important feature there, which is the positive event, which means that positive event has the most impact on my mood that I'm trying to predict. I hope I've been able to clarify that.
Yes, sir. How about the mean square error, sir?
Oh, the mean squared error. Yes, for mean squared error, the best value you can get for mean squared error is 0. So the closer to 0, the better it is. For mean squared error, you cannot have a negative value for mean squared error. So mean squared error ranges from 0 to over infinity. You can have infinity. You can have 1 billion mean squared error. That one is really, really bad. You understand? So the closer it is to 0, the better the feature, the better the model performance. So in this case, when they remove moving, they calculated the mean squared error. Let's say the mean squared error was like 0.9, or let's say it was 0.0001. That was very close to 0. While others were actually performing worse when they removed it. So it will continue to eliminate. The same principle is still going to happen. So it will just be eliminating all the features one by one, until the feature that was removed that gave the model the best performance is being considered the least important there. So the same principle occur. So all those things like mean squared error, mean absolute error, R squared, all of those things are called metrics. Metrics just means a measure of performance. Metrics is just a measure. How you measure a model performance is by using either mean squared error or R squared or mean absolute error, depending on the problem. Some can also use absolute accuracy. Some can use micro accuracy, macro accuracy. It depends, like in classification problem, you use macro and macro accuracy. In regression problem, you use R squared, mean squared error, or mean absolute error. Those are the metrics that you use to know how well your model is performing. I hope I've been able to answer your question well.
Yes, sir. I really appreciate, sir. Thank you so much, sir.
All right. Okay.
One
You're
more thing, sir.
welcome.
Hello, sir.
Okay. Yes, I'm with you.
One more thing. You made mention about the RSC and likewise
Yeah.
the physician,
The what?
the psychologist. The psychologist.
Yes.
I want to make a
Yes.
relationship between the two measures you. So now, which one comes first? Is it that we consult the psychologist about the data given, explaining to us that this one have an effect, this one have a lower effect, this one have higher effect, or is it that one come first, or the RFC?
RFE, right? That's a very good question. Well, the first thing that should come first is you consulting your psychologist. Your psychologist can give you clues on the features that you are supposed to collect when you are trying to collect your data. In the data collection process, you need to first of all go and meet your psychologist. Your psychologist is the domain expert, is the one that knows about what you're trying to predict. So you go and meet your psychologist. Okay, I'm trying to predict my mood based on different factors. What are the factors that you think are most important for me to collect? Your psychologist would then tell you based on his own knowledge, okay, external factors are very important for you to consider when you're trying to predict your mood. The atmosphere too is important. By external factors, I mean things that are happening to you, the things that people are doing to you. Your environment, such as your temperature, your air quality index, maybe humidity too can be part of it. The pressure, the probably the oxygen concentration of the environment. Your environmental factors too might have an influence. External factors like your phone usage too can also have an influence on your mood. Your heartbeat too can have an influence. Sleep quality can have. Your stress level can have. Your physical activity, how physically active you are, can have it. The number of steps you are taking every day. So your psychologist will be the one to tell you that these are the things that you are supposed to be collecting in your data collection process. So once your psychologist have told you all the things that could influence your mood, remember that individuals are different. So for you as an individual, you know the things that you do every day. So you have to discuss this with your psychologist. So your psychologist might ask you more questions. For instance, what are your habits? The things that you do every day. Maybe, for instance, you are a part of you are somebody that drinks. For instance, you drink. So drinking can also be part of the features that is there that could have an effect on your mood. Maybe in that case, you are going to be measuring the number of maybe bottles of beers you are taking every day, or the cups, the shots, how many shots of vodka you are drinking every day, depending on your lifestyle. So it's also very important to consult with your domain expert. After consulting with your domain expert, if you now want to start eliminating features to make your model as simple as possible, remember Occam's razor. Occam's razor says that the simplest answer is usually the right answer. So the simpler your model is, the better the performance of your model. So just because your model is very complicated, that does not mean that it's going to perform very well. So for that question, you should meet a domain expert first for the data collection process. And when you start analyzing it, you will begin to see the features that are most important using RFE, PSA, and correlation analysis. I hope I've been able to answer your question.
Very well, sir.
Good.
Hello?
So
Hello, sir.
okay.
So one
All
more
right.
question. One more question. The correlation table. Please, I want you to
Yes.
please recap how the
Eric.
mood correlates along the diagonal axis of the table.
Oh, okay. How they correlate diagonally, right? Yes, because they are the same thing. It's the same thing. Mood correlates with mood because mood is mood. One correlation. Sleep quality correlates with sleep quality because sleep quality is sleep quality. So it has one correlation. Sleep duration correlates with sleep duration. You can see, you will just trace it. You trace sleep duration on the horizontal, sleep duration on the vertical. You will see that they meet at 1.0 because sleep duration is the same thing as sleep duration. They have a perfect correlation. One is a perfect correlation. BPM perfectly correlated with BPM because BPM and BPM, they are the same thing. So there's a perfect correlation between those two things. So that is why on the diagonal axis, you are just seeing one, everything because it's the same thing. So using that same reasoning, we can all agree that when two measures are close to one, it's trying to tell us that they are very similar. That is, they are measuring the same thing. Like in the case of sleep quality and sleep duration, you would agree with me that the longer you sleep, the better your sleep quality. Somebody that slept for just 1 hour throughout the entire day, his sleep quality will be very low. which is true. But somebody that slept well for 8 full hours, his sleep quality measurement will be very good. Will be like 80% sleep quality because he slept for a longer time, which is true. But remember that sleep duration is not the only thing that determines your sleep quality. The number of time you slept in deep mode, in your deep sleep, your light sleep. There's also rapid eye movement sleep too. The number of time you wake up while you are sleeping, the number of interruption you had while you're sleeping, all of these factors contribute to your overall sleep quality. That's the reason why sleep duration and sleep quality are very correlated to 0.78, which is very close to 1. So what that is trying to tell us that having both sleep duration and sleep quality in the same model is redundant. It's like you are repeating yourself. They are measuring almost the same thing. I hope you understand what I'm saying now, and you understand how to interpret the correlation analysis confusion table. Have I been able to explain that well?
Yeah, sir. Thank you so much, sir.
All right. So I hope you people enjoy this class today.
Yes, sir.
Very
Please, I have a
well, sir.
question.
All right. I'm very glad. So in our next class, we are going to look at a real application of
Hello?
regression-based machine learning. And we
Hello,
actually
can you hear
open it
me?
up and see. Yes, I can hear you.
Okay, sorry, please, I have a question, sir.
Okay. What's the
I promise
question?
not to take it. Yes, okay, sir, please. It's on that principal component analysis. So when I was doing my
Yes.
undergraduate, I actually employed
Yes.
this principal component analysis. But I don't know if I did it
Okay.
rightly, so I want to ask you if it's what I did was correct. So I did a
Okay,
study
good.
that was trying to predict the possible factors responsible for health worker migration from health facilities in
Oh,
Nigeria. So I took a
okay,
bunch of
okay.
asked the market skill, I asked questions on some factors. Is it because of better
Good.
salary over there? I analyzed
Mm-hmm.
push and pull factors. So I wanted to well, at the end, I did the PCA and I brought
Yes.
out a few factors that explain more of the variance and threw away the other ones. But now, with you telling me the
Yes.
domain knowledge and all those other things, I'm not saying okay, probably PCA may not have been the best thing to have
Best.
done there.
Yes. Yes, that's actually true. PCA is an unsupervised learning technique. You understand? So it's just the machine is just going in and looking at angles from which the data has the most variation. That's what PCA is all about. It's just trying to capture as much variations in the data as possible. So
Mm.
the in the place where PCA reign supreme is if you are trying to visualize your data on maybe on a 2D graph, or if you are just trying to visualize it even on a 1D graph, a single dimensional graph, which is a number line, or a 2D graph, or you just want to visualize it on a simple 3D graph, and you have like maybe 20 features that you are considering. Obviously, you cannot visualize a 20-dimensional space. It's not possible. You can't even visualize a 4-dimensional space. The human mind can only see a 3-dimensional space. So this is where PCA comes into place. PCA will just create 3 new dimensions that captures the maximum variation in data so that you'll be able to see everything at once in 3 dimensions. So it's a dimensionality reduction technique. You understand? It creates new features. So it is not a direct feature selection method. You can just use it to reduce the dimension to 3 so that you can visualize it for people to actually see it, see everything that is going on at once. You understand? But in this method that you are saying, yeah, I'm trying to use PCA to rank it. So it's not a conventional method. It's not an advice method to use. So what I just did was I just multiplied. Look at what I did here. I multiplied the component importance by the explained variance. That's what I did to rank it, the feature. The component importance is just ranking. Like now, principal component 1 is the most important, followed by principal component 2, followed by principal component 3. That's the ranking of the principal components. Why the explained variance? That is, the explained variance is just the weight of each feature to each of the principal components. So when you multiply the weight of a particular variance to the component importance, you add that to the next component important, to the next important component, to the next important component, and then you add everything together. So using this method, you use it to rank each of the feature. This is not a conventional way for selecting feature ranking because it's unsupervised. The computer does not know what you're trying to do, does not know what you're trying to predict. You can notice that I completely dropped the mode feature. If you study this code well, you notice that I just dropped it. I just dropped the mode here in this X, and I ended up not using Y. I didn't use Y here. If you go through the entire code, you will not see where Y was even used at all there because it's unsupervised learning. And remember, in unsupervised learning, we are not considering the dependent variable, or the dependent variable might be there, but it's not going to have any special importance in the analysis whatsoever. So that is PCA. So instead of using PCA for your feature, is better. What another usefulness of PCA is just for you to know the number of components that is needed to capture at least 75%. Here is telling us 5. 1, 2, 3, 4, 5. 5 captures at least 70% somewhere here. So you can use that knowledge to know that, okay, it seems like 5 feature is just enough for you to select 1, 2, 3, 4, 5. You just select the first 5. Might have a very good effect for you. And then you can select script quality also, because you have talked to your domain expert. Your domain expert will let you know that sleep quality is very important. Do not eliminate it. I hope that has answered your question concerning your prediction of what is responsible for health workers leaving Nigeria for greener pasture.
Thank you very much, sir. But
Right.
is it possible for you to help me just look at the analysis?
Which one? For PCA
Like the one,
or
yeah,
RFE?
the one I already done. Yeah.
For which one?
That particular work I just
For
mentioned.
Oh, okay, like we should look at it together right now.
No, not now. Maybe later I'll send to you.
Okay, that will be later. Yeah, you can send me a personal message on that.
Oh, thank you very much.
Yeah, we
I'm
can
very
build
grateful.
it. We can book it. Yeah, we can book a session to actually look at it together. That's no problem.
Thank you very
All
much.
right. Thank you very much for attending this lecture. It was really nice to have you all here. So we see again the next class where we see a real life
Good evening, everyone.
AI application.
Hello,
Yes.
good evening,
Thank you
Dapo.
so much.
Yes, sir.
Hello. Oh, I'm so sorry. I don't know. My internet was just keeping not cooperating with me today. So sorry for joining
Okay.
late.
Oh, that's
So,
no problem.
do you think that with the pace at which you are going, 1 hour will be sufficient for us to cover your class, or do you think
Oh,
I expect by
the
30 minutes?
remaining classes will be very fast. Actually, this is the bulk of it.
Okay, okay. All right, that's fine. Thank you very much for your time. Thank you, everyone, for attending this evening. So,
Yes,
see you on Monday.
yes,
God's
yes,
grace.
yes. So this is the
Thank
foundation.
you.
That's why these classes are taking a lot of time.
So, we are done with the foundation now. So, we are starting the.
Yes, we are done with the foundation. So we will now start looking at real application of machine learning and see how it works.
Okay. That's fine. Thank you very
Yes.
much. Have a good evening, everyone.
All right.
Yeah,
All right
bye.
now. Good day, everyone.
Thank you.
Bye.